So, Dr. Pradhan, slowly all the participants are joining. It's 3:15 already here. So I think we should start now.
Okay. So yeah.
So let me give a brief introduction about you. So firstly, good afternoon, everyone joining, and who will be joining us. And this is Binay Karna from Asian Institute of Technology, and I'd like to welcome everyone on the behalf of Structural Engineering Forum at AIT. And today it's my honor to welcome our guest speaker, Dr. Nischal Pradhan, on the behalf of our forum. So Dr. Pradhan is a PhD from Hong Kong University of Science and Technology, commonly known as HKUST. He is currently working as consultant in different government and international projects, and his research works are mainly focused on the performance of bamboo structures through experimental and numerical simulations. So the results, he has already published quite a good number of papers through his research. So I'd like to hand over this to Dr. Pradhan for the next 1 hour session, and we'll be having Q&A at the end of the session. So Dr. Pradhan, welcome, and over to you. Thank you.
Thanks, Vinay, for introducing. Thanks for giving me this opportunity to present my research. So for the next 30 to 45 minutes, I'm going to go through my work as a PhD student back in Hong Kong. Okay, it's mostly about the performance of connections for bamboo axial members. Okay, so let's begin. I want to start with why we want to use bamboo structural material, right? So bamboo has quite a few advantages. For example, it grows very fast. It is inexpensive and sustainable natural material. It has excellent mechanical properties, and it is widely available where it is needed, right? So all the developing regions around the world is also the region where we see bamboo, right? For example, you can see a photo here where in the Philippines, where Base Bahay has built a lot of bamboo structures, okay? You can also find magnificent structures made out of bamboo in Indonesia, right? You can also see quite a few nice, quite a wonderful bamboo structure here in Vietnam as well, right? You don't even need to go that far, okay? So even in Thailand, there are quite a few magnificent bamboo structures, especially the ones that are made by Chiang Mai Life Architects, okay? So on the backdrop of these structures, so I want to focus on a particular issue that hinders a more widespread use of bamboo for structures, okay? And the main reason here is, among others, is lack of reliable connections, okay? Now, the reason why we don't have very good connections for bamboo comes from a large variation in geometric and mechanical properties of bamboo, right? So because this is a natural material, the diameter, thickness, everything can vary from element to element, right? So it's very hard to regularize such natural materials into structures. The second reason why we have such a challenge is because the bamboo culms have a weak transverse axis, okay? Which means the section is susceptible to longitudinal splitting, a typical failure mode, a peculiar failure mode of bamboo that you can see here, right? Now, there are a lot of connections that you can already see being implemented in the industry, okay? So you can broadly categorize them into two types. First of all, we have a lot of traditional connections, okay, that rely on skill and experience of craftsmen, which includes fish mouth connections that you can see over here, okay? This also includes lashing, okay? Otherwise, we have connections that are quite creative or proprietary in nature. Okay? So only the inventor knows how to design these connections, right? My goal as a PhD student was to come up with an engineered and standardized connection solution for by any engineer. Okay. Now, this is our proposed solution. Okay, so we have a proposed solution consists of multiple bamboo culms that are connected to gusset plates on either side with the help of bolts or dowels. Okay, so this is the implementation of the solution into a full-scale bamboo footbridge. And as you can see, the solution accommodates natural variability of bamboo culms. In particular, bamboo culms need not be of same diameter, right? And to take care of the peculiar failure mode by splitting, we use confinement by means of hose clamps, right? I will explain later on why this is very effective, okay? Right, so let's look at the performance of the proposed connections. So in this particular study, we examined 3 different types of connections, okay? The first one refers to a plain connection where we have a pair of bamboo culms connected to steel plates at both ends with the help of bolts, okay? The second type of connections have the same as the first, but we have hose clamps that confine the bamboo culms at either side of the bolts. And in the third type, we infill the connections with the help of mortar, cement mortar, okay? So let's take a look at how these connections perform. First of all, the plain bolted connections under tension loading exhibit longitudinal splitting failure, okay, which is marked by sudden drop in strength. And this type of failure is seen in all plain connections. Okay, you can change the length of the specimen, you can change the end length, right? Or you can change the loading direction. The failure mode is always longitudinal splitting, and this is brittle mode. Okay, so ductility is quite small. Okay, once you confine the bamboo culms with hose clamps, we eliminate longitudinal splitting. Okay, so this allows us to have very large plastic deformation of bolts, as you can see here. Okay, and if you look at the ductility, we now have a very large ductility of 7.34. Okay, this is by far exceeds the requirements of most building standards. Okay, so very few structures in the world needs a ductility as large as 7, right? The failure mode now changes to either culm damage or bolt fracture. Okay. If you look at the video here, what happens is once we have confinement, the specimen enters plastic states by yielding of bolts. Okay. And the plastic deformation is characterized by embedment damage and plastic deformation of bolts. As you can see here, the damage by embedment. And at ultimate stage, we see a combination of failures. It could either be a bolt fracture, as you can see here, or culm damage. Culm damage occurs in the form of crushing, okay, or row shearing. The crushing failure happens when the deforming bolts apply radial compression on the cross section, which ovalizes and therefore cracks the cross section, as you can see over here. You can see over here how the culm has ovalized and crushed because of the deforming bolts. A typical failure mode also seen in dowel, any dowel connection is row shearing, where a part of bamboo culm or the material comes out like this, right? Now, increasing the end length will improve the resistance against culm damage by failure, and as a result, we can have even higher ductility, 8.94. This is by far the highest we've ever seen. And we can achieve failure solely through bolt fracture. Okay. Now, if you infill the connections with the help of cement mortar, you can achieve a bit higher strength, but the mortar infill restricts bolt deformation. Okay. As a result, the ductility is somewhat lower than hollow section specimens without mortar infill. Okay. The mortar infill also eliminates crushing and row shearing, and the failure is by bolt fracture. Now, you have to realize that increasing the end length does not really improve the performance. Okay, so now if here I present all the test results that are normalized for easy comparison, and as you can see, the top row corresponds to plain bolted connection system, and you can see that the performance is really bad compared to confined or infill sections, right? So you have to realize that we are getting a magnitude of improvement here, like 2 to 3 times more strength, 2 to 3 times more ductility, just by adding a very small increase in cost in the form of hose clamps, right? So given this result, I would always choose to confine connections with the help of hose clamps. Okay. You can use infill to get a little bit higher strength, but you are losing again ductility in the process. Okay. So here we did some tests in cyclic tests as well, and you can see the typical cyclic response of plain bolted connection. So you can see how the bolts are deforming as we are applying cyclic loads. Now realize this, that the cyclic loads are very slow quasi-static type. Here I have increased the speed just to facilitate easy viewing. Okay. Now again, the ductility of plain bolted connections is very low, almost no ductility. You can say that there is no ductility here, right? Adding hose clamps improves the ductility by a lot, 2 to 3 or 3 to 4 times, right? Now, but for the cyclic testing, the ductility is again a little bit limited by early fracture of bolts. Okay, so the bolts we used were quite susceptible to fatigue damage, and if you can use a high performance bolt, you can get even a larger performance than what you see over here. Okay, and this is a typical response under of the confined specimen, right? So even higher strength, higher maximum strength, but a little bit lower ductility compared to hollow section without confinement. Sorry, with confinement. Now, if the monotonic tests did not really convince you, then the cyclic tests should convince you that plain bolted connections are really bad. Okay. In particular, the splitting initiates from the connection zone, and it propagates almost through the entire specimen. Okay. There is a common conception in the industry that the presence of bamboo nodes, the nodes in the gum, help restrict splitting, but this is not the case. And as you can see here in the result, the splits can propagate easily through the nodes. Okay, here also, very, very close, right? Now, if you add confinement, you can eliminate the splitting entirely to get a different failure mode, and in particular, damage mode in the form of embedment and failure in the form of bolt fracture. Okay. One of the bad, let's say, drawbacks of bolted connections for bamboo structures is in sense that it is susceptible to a lot of vibrations. Now this arises because of pinched hysteretic curve. What happens in particular here is during the low amplitude cycles, what happens is that during the loading stage, the bolt embeds into the bamboo culm wall and leaves behind a small cavity during the unloading stage, right? So this cavity enables low friction resistance path for future loading cycles. So basically, this is the first loading cycle, which damages the culm by embedment, and this creates a lower friction path for the future loading cycle, as shown by the dashed line. Okay, in the high amplitude loading cycles where the bolts have plastic deformations already, what happens is that during the unloading stage, the bolts do not straighten out. Okay, instead the bolts undergo rigid body motion, and which enlarges the culm wall cavity, as you can see over here, and as you can see in the figure over here. Okay, so this rotation enlarges the wall cavity, and it is observable over here along this line over here, along the both stages. Okay, again, similarly, the primary loading cycle creates low friction resistance path for the future loading cycle, and hence we have very high levels of pinching. Okay. Now, the most important aspect of these connections compared to, let's say, contemporary solutions in the field is that these connections are predictable. In sense, their yield capacity can be predicted using European yield model equations that were originally developed for timber. And it turns out these equations work very well for bamboo connections as well. In particular, the error in prediction is about 10% for monotonic specimens and about 15% cyclic specimens, right? So this means these connections are predictable, and this is very promising for rational design. In other words, we can come up with a way to rationally design these connections, similarly to what we see for steel structures or concrete, right? So any engineer can use these equations to design them. Okay, so the next part of my study comes up with a way to rationally design such connections. Okay, so here in this study, we propose a capacity-based design approach that manages the natural variability of bamboo columns and ensures high predictability and ductility of the connections. So we do this by proposing an original combination of grading, which refers to the removal of unviable and defective columns, use of multiple columns. For example, here you can see 4 bamboo columns are being combined into a single axial member, and adopting capacity-based design principles to establish a desired hierarchy of capacities. Okay. Now, first of all, use of multiple columns helps reduce variability. The reason being, in a multiple columns arrangement, it is very unlikely for more than one column to possess unfavorable values of geometry and material properties simultaneously. So the stronger columns compensate for the weaker, and the overall performance of the member averages out. Okay. So what it means is the variance, on the other hand, reduces. Okay. So in particular, variance of a multi-column member equals that of single column divided by the number of columns. Okay, so if you believe in this, then we can do a lot of different. We can see the magic happening right now. Okay, so in particular, let's take an example first. Okay, if you look at the tensile strength, the expected value of a single column is about 127.3 megapascals. The variance is about 521. So this variance reduces to 260.6 for 2 column, and again 130.3 for 4 column. So basically, in other words, the distribution or the scatter in the performance are narrowed down. Okay, you can see how it is becoming more and more defined as we are increasing the number of columns in the axial member. This has a very important ramification in design, and in particular, the characteristic values, which refers to 5th and 95th percentile, the design values, which refers to 0.1th percentile, and the material partial safety factor, which they all become less conservative as we start adding more columns to the axial member. Okay. So again, if you look at the partial safety factor, which is 1.58 for 1 column, this reduces to 1.18 for 4 columns, and the 5th percentile characteristic value equals 89.8 for megapascals, reduces to 108.6. Increases to 108.6 megapascals. Okay, so all these design characteristic values become less conservative. Okay, we implement this for all the other properties. We try out different methods, different distribution fits, because we don't really know which is the correct distribution. Okay. Now, on top of this, what we want to do is to establish the hierarchy of capacities. Okay, to get a reliable and predictable mechanical performance. So a typical axial member consists of 3 parts: bamboo columns, dowel connections, and gusset plate. So among these 3 components, the dowel connections exhibit yielding, which is predictable and ductile, that I showed in previous slides, and therefore they should be designed to fail first. Okay, the bamboo columns are brittle, and hence their failure is undesirable, and they have to be designed stronger. The failure of gusset plate is also undesirable, because in a typical structure, the gusset plates connect multiple axial members together. Therefore, the failure of gusset plate can result in structural collapse by loss of joint integrity. Therefore, we don't want gusset plates to fail as well. Okay. So, in other words, the design capacity of dowel connection equals or exceeds the design load effect acting on the axial member, and everything else is designed at the overstrength of the design yield capacity of Dowel type connection. Okay. The overstrength factor consists of a combination of three partial factors, gamma SC, gamma N, and gamma M, where gamma SC accounts for the variability in the experimental distribution or the real distribution of the connection yield capacity. Gamma AN accounts for the error in analytical prediction of 5th percentile using the European yield model equations, which we know are very accurate in our past experiments. And finally, gamma N accounts for safety factor of resistance, which we provide to ensure a desired probability of failure. Okay. Now, to calibrate this curve, these partial factors, we only need the experimental distribution of yield capacity. So to do this, we perform experimental tests. Okay, here we perform for each type of connection about 15 tests for each type of connection. Okay, so this is a typical response of focal member under tension, and as you can see, elastic response followed by bolt yielding, followed by large plastic deformation, and then failure by means of culm damage and or bolt fracture. Okay, at the top. Okay, so elastic response, bolt yielding, large plastic deformation, failure by culm damage or bolt fracture at ultimate stage, and then failure. So again, notice the ductility of the specimens, which is about 7.44. This exceeds the requirement of most building codes for conventional materials. So we test 15 of them to get the experimental distribution of the yielding. Okay, the analytical equations predict 26.24 kilonewtons as the yield capacity, and similarly for compression. Okay, if you look at the compression results here again, you can see how the specimens are deforming. This particular specimen also fails by buckling at the maximum stage, right? The ductility is about same, 7.94. And from this, by testing 15, we get the results for compression. This is a typical response on of mortar infill specimens in tension. You can see again, elastic deformation, yielding, large plastic deformation of bolts, and then failure at ultimate stage. The mortar infill restricts deformation, therefore the ductility is a bit lower compared to hollow section specimen. Okay, and this is the response of mortar infill specimen under compression. Okay, so you can see how the specimen is deforming. This particular specimen also fails. This specimen exhibits the highest developed maximum capacity of 176 kilonewtons. So this is by far the highest we've ever seen in the literature. Okay. Again, the mortar infill restricts bolt deformation, so ductility is a little bit lower compared to hollow section specimen. The connections exhibit quite a significant amount of strain hardening, as you can see over here. Okay. So by doing this test and getting all the population sample statistics, we can finally calibrate the partial factors, and you can see the values over here. Notice that the gamma AN is almost equal to 1, which means RVK is almost equal to RVK as in the analytical value almost equals the 5th percentile characteristic experimental value. Okay, so what this means is that the analytical approach can indeed predict the experimental yielding, and this is partial verification of proposed approach. Now you have to keep this in mind. Keep in mind is that the analytical approach uses the material strength data for single culm specimens, and we can show that we can see that by reducing the variability with the help of multi-culm members, we can use the single culm statistics to predict the performance of multi-culm members. Okay, so this is very important verification, showing that the proposed approach works. Okay, You can also see that gamma m, which refers to the safety factor of resistance, almost equals 1.31, which is equal to that the value given by the Eurocode for timber connections. Okay, the partial factors are larger for mortar infill specimen. You can see for almost all the other partial factors. The reason being, mortar infill specimens have larger variability compared to hollow section. Just because they are more difficult to fabricate, they have more construction errors, they have more things that are variable, right? So that's why the factors are even larger for mortar infill specimens, right? So now with this study, we have a way to rationally design such connections that ensures failure by yielding of bolts before other components. Thereby, we can achieve axial members of high predictability and ductility, right? Now, let's figure out how to analyze the performance of such structures made by such axial members. Okay, so let's go back to the footbridge that we talked about in the beginning. Okay, so here you can see the entire axial members are made out of the structural, entire structure is made out of the proposed axial members. And you can see how we assemble them. Okay, so we first of all assemble truss A. One side of the truss, we assembled the other side, and then we erected them together. So we did this entire assembly within a span of few hours using untrained people. Okay. So this shows that you can use this this solution for rapid assembly in the site as well. Okay. Yep. Right. Okay, so now let's figure out how to analyze the performance of such structures. Okay. Now let's take a look at the response of the axial members again. The axial member with Dowel type connection can be modeled using a serial arrangement of springs. Okay. The elastic response of the axial member is it consists of a combination of springs that represent the stiffness of bolted connection, the stiffness of bamboo culm, and the stiffness of bolted connection again. Okay. The plastic response is characterized by bolt plastic deformation and embedment damage, as you can see here. And this is modeled using additional springs, KCP, okay, on top of plastic response. So we can calibrate the values of all these parameters by combining the axial member test with the material strength test. Okay. So by combining these two experimental tests, we can back calculate all these values. And once we do this, we can come up with a way to model such axial members in SAT 2000. First of all, the axial member the elastic response is modeled using a single frame element of stiffness KE. The plastic response, on the other hand, is modeled using plastic hinges. And these hinges perform in a way similar to FEMA 356 hinges, which is well known to everybody, right? And as you can see, the proposed SAT 2000 model perfectly reproduces the experimental bilinear curve, right? Once we have validated the performance of a single axial member, what we do now is we extend the response, the model to model the response of bamboo culms or the axial members of rest of the members of the bridge. Okay. The model accounts for bamboo culms of different number, two bamboo culms or 4 bamboo culms, and also bamboo culms of different length. Okay. Now the idea is by incorporating this model into every single element of the bridge, we can try to model the nonlinear response and damage progression of the truss structure. Okay. A particular peculiarity with the design is that the gusset plates were quite thin. Okay, so the bridge is also susceptible to failure by gusset plate, and hence we also modeled the yielding of gusset plate with the help of it's the same lump plasticity or the plastic hinge approach. Now the gusset plate modeling is standard in nature, we use Hong Kong Code of Practice. Okay, so you can use any different codes as relevant. Okay, so here we can see how the bridge, the truss performs in the experiments. So we apply a point load at the center of the bridge, as you can see. Right, so let's figure out what's happening here, okay? So when we apply the point load at the center of the bridge, what happens is that the bridge enters the plastic stage by yielding of bolted connections over here. Okay, you can see that the bolts have some yielded, and these bolts are over here at nodes A6. Okay, as we load the structure, the plate at A5 buckles, and upon buckling of plate A5, we can see out of plane deformation of the top nodes A5 and B5. You can see how the plates have buckled here. Okay. You can see here I show you the plots of the numerical response along with the experimental, and you can see that the numerical response can indeed give an accurate performance or the accurate prediction of the experimental. Okay. In particular, the numerical response can also predict the order the order of failure modes. That is, first failure mode by yielding bolts, which causes the bridge to enter the plastic stage, and collapse by means of buckling of plate A5. Okay, which results in a large out of plane deformation of the node A5. Okay. So let's go to the conclusions of my research. Here we proposed an alternate connection solution for bamboo structures, and here we showed how beneficial the confining actions can be on the performance of connections, dowel connections in particular, right? We showed that the dowel connections can indeed be predicted rationally by European yield model equations, which paved the way for development of a rational method for designing such axial members, right? The method consists of an original combination of grading, use of multiple culms, and capacity-based design principles to achieve predictable and ductile behavior. Finally, we developed an approach to simulate the response of such structures with very high accuracy, or very good accuracy, right? So thank you for listening to my presentation. Especially sincere thanks to my supervisors, Ilias Dimitriakopoulos and Camelina